Welcome back. Chapter 2 BJT Amplifiers. Topic is BJT DC analysis. Okay, in the last class we had seen collector to base bias circuit, and if you take collector to base bias circuit, what was the stability factor we got? We got stability factor S is equal to 1 plus beta into RB plus RC divided by RB plus 1 plus beta into RC. This is what we got, right? Just a minute. Right now, this is what is our circuit. This is RC, RB, VCC, and this is the base current. This is collector current. The current which is flowing through this is nothing but IB plus IC. This is what we had seen, and this is VCE. We are speaking about Q point. Q point is nothing but VCE comma IC. Right? Ideally, we are expecting stability factor value to be 0. That is what I told, because the definition of stability factor is nothing but the change in IC due to IC naught when VBE comma beta constant. Right? Ideally, I don't want to see any change in IC due to IC naught. Therefore, I am expecting S to be 0. But practically it is not 0. We got some value, right? Which is not 0 value. Maybe if I make it simple, that is easy to remember. But remember, we have to remember this stability factor. Now, if you see, if 1 plus beta into RC very much greater than RB, typically this is true. 1 plus beta into RC is very much greater than RB. At least 10 times. If it is more, you can take it as very high value. Then, if this is very much greater than RB, can I neglect RB? Yes. If I neglect RB, then it is left with 1 plus beta into RC in the denominator. Then 1 plus beta into 1 plus beta and 1 plus beta, both will be cancelled. Then RC by RC, 1 plus RB by RC. Then your stability factor will be 1 plus RB divided by RC. This is derived formula. This is original formula. This is derived formula. Now, maybe if I consider the derived formula, right? Now, what value of S we can get which is minimum? I can say we can get S is equal to 1. That is what is the minimum value we can get, provided either RB is equal to 0 or RC is equal to infinity. When I say RB is equal to 0, what does it mean? When I say RB is equal to 0, it is short circuit. right? Therefore, the base is shorted to collector. When base is shorted to collector, what does it mean? We are going to apply input, small signal input, which I am going to explain later. Then the same input you are applying here. If it is short circuited, then your output will be equal to input. If output is equal to input, it is a wire, let us say, then what is the importance of having transistor, resistor, power supply? No, right? Therefore, it is redundant. The circuit what you will have if RB is equal to 0 will be redundant. Then V0 is equal to Vi. V0 is equal to Vi. It is a wire. It is simply a wire. But redundantly the circuit is connected. Therefore, if it is a wire, V0 is equal to Vi, but your output voltage and the output DC voltage, what you are getting from input DC voltage is independent of temperature, obviously, right? Therefore, we are speaking about stability factor to be minimum where my output current is independent of reverse saturation current, ultimately which is what is changing the Q point. Therefore, I want to have Q point to be stable. To have Q point stability, saying that RB is equal to 0, therefore you will get minimum S value. If RB is equal to 0, your AC gain is affected. Your AC gain is becoming less than or equal to 1. Therefore, that is not the practical solution. Mathematically, it is giving solution, but it is not giving you practical implementation. Now, maybe RC is equal to infinity. When RC is equal to infinity, then also S is approximately is equal to 1. Then, if RC is equal to infinity, it is open circuit. When this is open circuit, there is no IC, there is no IB. Your VCE will be 0, everything will be 0, right? If everything is equal to 0, then what is change in IC? There is no change in IC. If IC is equal to 0, 0, what is change in 0? 0 only, right? That is what it is saying, you will get minimum stability factor provided RC is infinity. Is that practical? Mathematically it is giving two solutions, but both are not practical. But if you ask me practically, people choose S value in the order of 10, 11, 12. That is what is okay. When I say S value is equal to 10, what does it mean? The change in output current will be 10 times of change in reverse saturation current. We know that the reverse saturation current will be changing in the order of microampere, then 10 microampere. If you take absolute current in the order of milliampere, out of milliampere of current, tenths of microampere of current change is acceptable. Okay. Therefore, this is what is collector to base bias circuit. Okay, which has negative feedback. Now, this is what is negative feedback resistor here. This is what is negative feedback resistor. This is providing negative feedback. Okay, take it. Already the circuit is there with you. These two are there with you. Only have to write this condition and then say this is what is your derived formula. And you can say typically people take an order of 10. This is what is typical value. Okay, after this third circuit, the name is self bias circuit. This is the last one from DC analysis. Okay, now actually this is also called as self bias circuit, but as I told you, two names are not given for the same one name is not given for two circuits. Therefore, this is what is given with the name collector to base bias, and the third one is self bias. Okay, the circuit is this is IB, this is IC, then this is output voltage VCE, and it is having beta. Now the operating point Q is nothing but output voltage VCE comma IC. This is what is our operating point. Then where is feedback resistor? I think we had seen this, right? I told when I speak about CE with RE amplifier to improve AC gain stability. Remember, whether it is AC gain stability, operating point stability, whatever it may be, wherever you want to improve stability, we have to incorporate negative feedback. If you incorporate negative feedback, the stability will be improved automatically. Okay. Therefore, that time when I speak about CE with RE amplifier, AC gain stability, now this is for Q point stability. Therefore, this is negative feedback resistor. This is what is giving you negative feedback. Okay. Now, let's see how it is providing Q point stability. First of all, what is Q point? Output voltage comma output current. If IC is constant, obviously VCE will be constant. But we know that your IC is changing due to temperature, right? If I write the same thing, whatever we have, we know that IC is equal to beta into IB plus 1 plus beta into IC naught. And it is function of IC naught comma IB comma beta, and all are depending on temperature, right? If temperature changes, your IC also changes. But we know that if IC is changing, just listen, don't write anything. If temperature increases, then IC is increasing. When IC is increasing, the same current is flowing through transistor. You can say this is IE. What is IE? Therefore, this is nothing but your IE. What is IE? IE is equal to base current plus collector current. Therefore, this is IB plus IC, right? Therefore, now tell me, if IC is increasing, then IE will increase. When IE is increasing, same current is flowing through RE, which is nothing but your feedback resistor. Then the drop across RE will increase. When the drop across RE is increasing, that is nothing but your emitter voltage. Therefore, this is nothing but your emitter voltage. This is emitter, base, and this is collector. And this is what is your VBE. Therefore, tell me, when emitter voltage is increasing, then what about your VBE decreases? When VBE is decreasing, IB decreases. When IB is decreasing, your IC will decrease. Due to temperature, if IC is increasing, then the same current is flowing through RE, then the drop across RE will increase, then emitter voltage will increase, your VBE will decrease, IB will decrease, IC will decrease. I told you, right, the bias whatever you are getting, VBE, that is what is controlled now, or that is what is self-corrected. The VBE value is self-corrected to compensate the change in IC due to temperature. Okay, whatever I explained here, the same thing I can draw using flow chart. That is easy to remember and easy to explain as well. Okay, now if you take the flow chart, temperature increases, then IC naught increases, IB increases because of VBE, and beta increases. All three increase IC. Now, this is what is due to temperature. Then when IC increases, now negative feedback is coming to picture. When IC is increasing, what is IE? IE is equal to IC plus IB. Therefore, IE increases. When IE is increasing, voltage at emitter. What is voltage at emitter? IE into RE. That is increasing. When voltage at emitter is increasing, Then your VBE, what is VBE? Voltage at base minus voltage at emitter. VBE decreases. When VBE is decreasing, IB decreases. When IB is decreasing, IC decreases. Therefore, overall, your IC is almost constant. Not absolutely constant, almost constant. As I told you before, qualitatively I cannot explain. IC is increasing due to temperature, yes. But how much is the decrement of IC to compensate the change in IC because of negative feedback? That I cannot explain. I know that definitely it will decrease, but how much it is decreasing? Is it exactly compensating the change in IC due to temperature? That we cannot explain qualitatively. For that we need to do mathematical analysis, which is nothing but finding the stability factor here. Okay. Take the flow chart. Then let's get the equation using KVL, and we can substitute the fundamental equation of your device. Then let's differentiate. It is similar to the collector to base bias stability factor derivation. Then we need to find what is the stability factor, and we can compare between collector to base bias and then self bias circuit. Okay, you take the circuit and take the flow chart. I'll give 1 minute time more. The negative feedback is due to that RE only. If RE is not there, there is no self bias of VBE. Over. Okay. Now, tell me input KVL. VCC is equal to the drop across RB plus the drop across VBE plus the drop across RE, right? VCC is equal to drop across RB is nothing but IB into RB plus drop across transistor VBE plus drop across RE, that is nothing but IE into RE, right? Then you substitute, therefore IB into RB plus VBE plus what is IE? IE is nothing but IB plus IC. IB plus IC into RE. Can I take IB common? If I take IB common, I will get RB plus RE plus VBE plus IC into RE. This is what is VCC, right? Then if you take this as star implies what is IB? We already did it, right? Therefore, what is VCC? VCC is equal to IC minus 1 plus beta into IC naught by beta. This is nothing but IB value into RB plus RE, RB plus RE plus VBE plus IC into RE. I think now you can differentiate this, right? Therefore, we know that S is defined as change in IC due to IC naught when VBE comma beta constant. Now differentiate this with respect to IC naught and tell me what is the stability factor. Definitely this time I will not do, we have to do it. I have done already for collector to base bias circuit, exactly the same way we have to calculate for stability factor. Yes. Now just differentiate this equation with respect to IC naught, keeping VBE and beta constant, then you will get stability factor from this equation. I will give you 30 more seconds to wait. over, okay. Now after differentiation you will get stability factor S, which is similar to collector to base bias, 1 plus beta into RB plus RE divided by RB plus 1 plus beta into RE. This is what is stability factor S. Is it 0? No, ideally it should be 0. But in this case also it is not 0, which is non-zero. Therefore, absolutely your IC is not compensated because of negative feedback. Ideally we are expecting S to be 0, right? Now, similar to your collector to base bias, if, to make it simple, 1 plus beta into RE is very much greater than RB. If this is true, then can I neglect RB? Yes. Then 1 plus beta will be cancelled. Then RE by RE, 1 plus RB by RE. Therefore, then S value will be in the order of 1 plus RB by RE. Practically the minimum value is 1, but provided when RB is 0 or RE is infinity. Those are all not practical solutions, because when RB is 0, it is short circuit. Means the VCC is applied directly to your base. Then whatever input you apply, because the power supply will override the input. Or even though you are applying input, that input will not propagate to your output. Therefore, your output is 0 for the input. Therefore, no gain. Mathematically, it is saying the solution to have minimum value of S, but practically, if you apply that condition, that is disturbing your AC gain or AC analysis. Okay, that is fine. Similarly, RE infinity. What do you mean by RE infinity? When I say RE is infinity, open circuit. IE is equal to 0. IC will be 0. IB is 0. Transistor is entering into cutoff. First of all, the state of the transistor is changed. Therefore, those two are not ideal values, practical values. Typically, people choose 10. This is what is the typical value. Therefore, I can say this circuit, whatever Q point stability we are getting from self-bias circuit, exactly similar Q point stability or same Q point stability value we are getting from collector to base bias circuit. Therefore, either one of these two circuits we can use where we are getting Q point stability, not only keeping the transistor in active region, which is our required region for amplification, and Q point is also stable from both the circuits. Both collector to base bias as well as self bias circuits, both are giving stability. But practically people use self bias circuit, not collector to base bias circuit. Practically people use self bias circuit, not collector to base bias circuit. Why? Now, if you see with respect to DC analysis, right, both are exactly same, I can say in that way, assuming both are giving same stability factor. Then why people use only self bias circuit? Why not collector to base bias circuit? To understand why people use only self bias circuit, why not collector to base bias circuit? For that we need to add AC signal coupling on top of the DC signals what we are dealing now from DC analysis. Therefore, that is what is next topic, I can say, AC plus DC or DC plus AC analysis, which we need to do. Till now we did DC analysis separately, AC analysis separately. Now this is the time to combine AC plus DC. That will explain why self bias circuit is used practically rather than using collector to base bias circuit. Okay, just give me some time, then I will explain why this circuit is used practically. Okay, before going to that, now write down practical self bias circuit. Yeah, this is also self bias circuit, but I want to correct something to make the transistor in active region easily. Therefore, there is a split of resistor RB into R1 and R2. That is what is making that is what is making that is what is helping the transistor to keep in the active region. You can say practical self bias circuit. This is also practical. but in realistic scenario people use this only, practical self bias circuit. This is what your operating point, VCE comma IC. This is what is the practical self bias circuit. Instead of using single RB where the voltage drop across RB is equal to the voltage drop across RC plus VCB. Okay, VCB should be positive and the drop across RC, that is what one thing. Therefore, if you add these two, that is what is the drop across RB which we are expecting. Okay. I can say both are equivalently same. Maybe if I apply Thevenin's theorem for this R1, R2 and VCC combination, then this is nothing but load for R1, R2 combination along with VCC. If you exclude the load, find the voltage across this, that is VThevenin. Then exclude the load, impedance seen from output port is nothing but RThevenin. Then we can apply, if you apply Thevenin's theorem for VCC R1, R2 and then transistor is nothing but load for your circuit, then what you get, this is nothing but VThevenin and this is RThevenin both are same only, right? Here VCC RB, but here VThevenin RThevenin, right? Both are same. Therefore now this is what is your VBE and that will define IC. Therefore you will get VCE and this is IB. Okay. Now what is VThevenin? The VThevenin value is, remember in the examination this will be given as a DC circuit. If this is what is given as a DC circuit, to solve IB and IC, that VCE, first of all you need to transform the VCC R1 R2 into VThevenin RThevenin. That will make that is easy to solve, else it is difficult to solve. We cannot solve the problem easily, right? Therefore if you make it like this, then what is VThevenin? VThevenin is equal to here R2 divided by R1 plus R2 into VCC. Then what is RThevenin? RThevenin is equal to R1 in parallel to R2. Why? Because what is RThevenin? We have to short VCC to ground, then R1 in parallel to R2. Your methodology of VThevenin, RThevenin, which is nothing but R1 R2 divided by R1 plus R2. If this is what is given, as this is what is given, if you see the problems, you will understand. Convert into VThevenin RThevenin and write input KVL, you will get the answer. Sometimes we need output KVL to get the answer, then we can apply. Okay. Take the practical self bias circuit. With this I can say DC analysis is over. Okay, it's done. Now the next topic, DC plus AC analysis. DC plus AC analysis. Okay, now I told you, right? Just listen, before that you can write down. You take amplifier, therefore when I say, now we are coming to end in the case of BJT amplifiers. Okay, almost done. When I say BJT amplifiers, right, we separated the amplifier into AC analysis problem or AC circuit. I can say AC circuit or DC circuit. Right, we analyzed both of them separately. For AC signals, the circuit what we have taken, from that we calculated all AC parameters, and for DC analysis we considered a DC circuit, then we did input KVL or output KVL and calculated Q point stability using stability factor S. Now tell me, what is the conclusion? The conclusion is, let us say, I can say this is what is our conclusion. Conclusion is, when I say AC circuit, what are we choosing? The AC circuit is nothing but what? This is your CE amplifier. Let us say, out of so many configurations, we are choosing common emitter amplifier because, that is what is giving you more power gain. CC amplifier is acting as a buffer amplifier for voltage amplification. CB amplifier is acting as a buffer amplifier for current amplification, right? But CE amplifier, this is what is giving voltage gain as well as current gain, therefore power gain. Therefore this is what is best suitable for the amplification, whether it is voltage amplifier or current amplifier. But ultimately we are speaking about voltage amplifier, therefore this is what is core of your voltage amplification, with which we are getting more voltage gain, and impedance matching that we can get using CC amplifier, that we have seen already. Fine. Now in the case of DC analysis, we want Q point stability. Not only keeping the transistor in active region, we want Q point stability. Whatever operating point we set, that should be stable. That should not change with respect to temperature. If it changes, then we will see distortion, because the AC swing what you are having about the DC voltage what you set, if the DC voltage is changing due to temperature, the swing about the DC voltage that will be clipped to one of the voltages what you have, then that is what is called distortion, which we don't want. Then we have chosen self-bias circuit. Therefore, from DC analysis, self-bias circuit. From AC analysis, we need a common emitter amplifier. That is what we need, right? Now, listen. Therefore, I am starting from DC circuit. Therefore, this is what is our DC circuit. What is DC circuit? Self-bias circuit, right? This is what is our self-bias circuit, okay? Collector, emitter, base. Then what is AC circuit? Therefore, from DC analysis, we want self-bias circuit. From AC analysis, what do you need? For AC signals, I want common emitter configuration. This is my load, let us say RL, and this is what is my input voltage, Vi. Therefore, this is collector, emitter, base. Basically, this is what is our self-bias circuit. And this is what is CE amplifier from AC analysis. common emitter configuration. Now let me combine these two. Just listen, don't write, listen. Therefore now I am giving you DC plus AC circuit. This is what your final circuit. This is what people call as BJT amplifier, which has both DC operating point and which has stability, or which has ability to amplify the input signals what you are going to provide. Then first of all we have to take the DC circuit. Before applying the AC signal, first of all transistor should be ready for the amplification. Therefore it should be in active region and the Q point should be stable. Whatever operating point you set, that should be stable. On top of the DC voltage we need to apply AC signal. This is RC, R1, R2, RE, right? Now we know that here the VCE whatever we have, it has some DC voltage, right? It has some DC voltage. Then I need to apply input signal here, right? Already it has some DC voltage, that is on V Thevenin, R Thevenin, using Thevenin's theorem. That is on V Thevenin, R Thevenin, which is what is defining your IB, right? Therefore now how to apply AC signal on top of DC signal? Remember, wherever you want to couple AC signal on top of DC signal, which is what is set by R1, R2, means whatever signal you apply from external source, we should not disturb the DC operating point what you set, or DC bias voltage what you have from the input circuit, that is VCC R1 R2 combination. Then there should be a capacitor. Capacitor will do the job of coupling AC signal on top of existing the bias voltage set by the local circuit or local R1 R2 VCC. Okay, therefore people add capacitor. Therefore this is what is coupling capacitor CC, right? Okay, or I can say capacitor at base. That this is what is the signal whatever you want to amplify. This is what is, like when I say this is what is VI. Okay, therefore whatever AC signal you want to amplify, let us say this is what is having 0 volt, then on top of that the signal whatever you want to amplify, that is what is applied. Then the capacitor is the one which is what is going to couple the AC signal on top of the DC voltage at the input, which is V Thevenin what we are getting. On top of that it will be coupling and then applying to your transistor. Okay, that is fine. Now coming to and do you want RE during AC analysis? Do you want any feedback? No, we don't want any feedback. If you have feedback, that is nothing but CE with RE amplifier. When I say that is what is CE with RE amplifier, remember that will decrease the gain. Your AC gain stability will be improved, but I am not interested for AC gain stability. I am interested for AC gain. I want maximum gain. If I want maximum gain, I don't want feedback here. Therefore, I don't want RE, but I want RE for DC signals. I want RE for temperature variation control, but I don't want RE for the signals what you are applying at the input to amplify. Therefore, this is not low frequency. It is not zero frequency. It is what is little bit higher frequency, 20 Hz to 20 kHz. Let us say audio amplifier. Therefore, it is definitely more than 20 Hz. But the temperature change, whatever you have for DC circuits, the collector current change is very low frequency, which is not of 1 Hz, 2 Hz. Therefore, for that we need feedback. For the AC signals, we don't want feedback. Means for AC we don't want feedback. For DC we want feedback. What to do? Just add a capacitor. This is what people call it as bypass capacitor. What is the job of bypass capacitor? It is going to bypass RE, or for AC signals you can say short circuit, then RE won't be there, negative feedback won't be there, then it is equivalently connected to ground, then common emitter configuration you will get maximum voltage gain, right? Then output side, you will get DC voltage, on top of DC you will get AC. But I want to apply directly AC signal to the load. I don't want to apply any DC voltage to the load. If I don't want to apply any DC voltage to the load, then you block the DC using capacitor, then you connect load here. Therefore, this is what is your load and this is what is your V0, because capacitor collector, therefore you can say CC. Remember, this is what is your final amplifier, which has both DC as well as AC. The black portion is representing DC circuit, which is cell bias circuit, and the blue one which we added on top of the DC circuit, that is what is nothing but that is what is going to give you under AC analysis, or for AC signals you will get common emitter configuration. Okay, you take it. I'll explain a little bit about the DC plus AC circuit. Therefore, you'll get some feel where yes, this is what is true. We can take it, and then I'll name the circuit. What is the name of this amplifier? Then I can stop. Maybe you have 1.5 minutes or 1 minute to stop this session. Then we can continue in the next section. Okay. Thank you.